Hello and welcome to Beyond the Shadow, exploring the great North American eclipse of 2024. Specifically, we'll be talking about the total solar eclipse taking place on April 8th of this year. Today's program is brought to us by NASA Nebraska Space Grant. My name is Michael Sibbernsen. I am a university educator for physics and astronomy. I'm also the director of education at Branched Oak Observatory. I'm actually in the Kunkel Family Multi-Purpose Center here at Branched Oak Observatory filming this program. And if you've never had a chance to visit Branched Oak Observatory, just send me an email. Give me a call. I'd love to take you on a private tour. And if you're an educator, I'd love to have your class come on out and visit us sometime and explore the night sky. Today's program will be exploring this amazing eclipse that is taking place, what we will see inside and outside of Nebraska. I'm sure we'll find some fantastic information that you'll be able to use on your own, for your family, your friends, and again, if you're an educator, you'll be able to share with your class as well. Before we get started though, of course, safety always comes first. We will be talking about observing an eclipse, looking at or towards the sun. Viewing the unobscured or partially obscured sun without proper protection, even for a short amount of time, can cause permanent eye damage. Be sure to take proper precautions during a solar eclipse or during any solar viewing activities. A little bit later, we'll be discussing some methods to indirectly and directly observe the eclipse and observe the sun. Techniques, equipment that can be used not only during the eclipse, but also really anytime. So you'll be able to take your students out and do what they were always told never to do, and that's to look at the sun. In this case, of course, we are doing it very, very safely. The universe. The universe is vast. At first glance, it may appear to be forever unchanging, but nothing could be further from the truth. The moment the universe came into being, it was expanding and growing. Energies cooling into gases, those gases condensing into stars, forming gigantic galaxies with stars of various sizes, stars of various temperatures and colors. The very large, hot blue stars living in a strangely short life, ultimately expanding, collapsing, going supernova, throwing themselves, their own materials, into the interstellar medium. Those materials then becoming the sustenance for new stars to form. And if there's enough material left over, perhaps even into planetary disks, forming new solar systems like our own. Now, one might think that these great changes in the universe would be privy only to professional astronomers living on mountaintops with giant observatories, but that's absolutely not true. You too can observe these amazing changes in the universe, particularly motions here within our own solar system. For example, throughout the evening, you can see stars rising in the east, traveling in an arc across the south, in the north, actually making circles around the north celestial pole. Ultimately, the stars that are far away from that NCP will go down in the west. This is just an illusion called diurnal motion, caused by the rotation of the Earth on its axis, and what we see from our point of view. As the Earth orbits around the sun, we are privy to different parts of the Milky Way. In other words, throughout the year, we see the sky change as well, particularly in the south. From the southeast to the southwest, we will see all new, different constellations. And in the north, they change their positions dramatically around the north celestial pole. Of course, the stars aren't the only things that are moving in the sky. The moon the sun and the planets as well. They travel across a path in the sky called the ecliptic. The ecliptic is essentially the plane of the solar system. So if you're ever looking for something within our solar system, it will be somewhere on this plane. And if you're fortunate and you go outside, you might see 1 or 2 planets along the ecliptic. And if you're really fortunate, you go out at just the right time, you may see a number of planets all lined up on the ecliptic, nice and close, like a planetary parade. This is called an alignment. This is an alignment from January 26th of 2023 with Venus, actually Saturn down here, Saturn, Venus, Neptune, Jupiter, the Moon, Uranus, and Mars. So many of the unaided eye planets and a few planets that you would need to use a telescope to be able to see. A little bit later in today's program, we'll be discussing another planetary alignment that you may get a chance to see. Actually, it's a little different. It's a very special planetary alignment. And you'll see why it's special here momentarily. Now, since each one of those planets orbits the sun at a different rate depending on how far it is from the sun, they have their own independent, unique motions along the ecliptic, and sometimes one can catch up with the other. And you'll have 2 planets get very, very close. And when that happens, it is called a conjunction. Here is a fantastic conjunction that's coming up very soon, August 14th. So you may want to write this down on the calendar. You can either go on out earlier on August 13th in the evening, or if you really want to see Mars and Jupiter as close to each other as possible, then go on out the following night, after midnight of course, on the 14th at 3 a.m., and you will get to see these 2 planets extraordinarily close to one another. Of course, it's just an illusion. They look like they're close. From the side, however, they're actually about 360 million miles away from one another. But from our point of view, they look close. How close? Well, do this for me. Hold your hand out at arm's length, stick your little pinky out like this. And it doesn't matter how old you are, how tall you are, it works for everybody pretty well. The width of your pinky is 1 degree of arc. That's essentially a measurement of angular length in the sky. 1 degree of arc is made up of about 60 arc minutes. 60 arc minutes. Jupiter and Mars will be 20 arc minutes apart. That's right. 1/3 of a pinky width. 1/3, that's how close these will appear in the sky. And if you have a telescope with a pretty good magnification capability, you will still be able to capture both of these planets in the same field of view. What a wonderful thing to watch for. Now that's close, but can these planets, or a planet and the moon, can they get even closer? And the answer is yes. When we have an object with a smaller apparent or actual angular size moving in front of an object with a larger apparent angular size, it is called a transit. Now this is, of course, the sun, and over here we see some sunspots, but that spot right here, that's not a sunspot. That's the planet Mercury. This was the transit of Mercury on Monday, May 9th, 2016. Yes, you could actually see Mercury traveling across the sun. And if you did not get a chance to see this, there's another transit of Mercury taking place on May 7th, 2033. Yes, I know it's a ways off, but certainly something worth waiting for. What an amazing thing to see. That was our transit, in this case, a transit of Mercury. Now, flip the script here. When we have an object with a larger angular size obscuring an object with a smaller apparent angular size, it is called an occultation. Right now, it's very popular to look for asteroids that occult stars. In this case, this is a lunar occultation of the star Aldebaran. Aldebaran is the eye of Taurus the bull. And I know it's very difficult to see the edge of the moon there, but watch Aldebaran right here. This is a video. Very soon, it's just going to wink out of view. There it goes. I'm going to show a close-up here in just a moment. As the moon moves across, that star is occulted and disappears. Now we can't even see that dark side of the moon, but very soon, there it goes. The moon moves at about a half a degree every hour, and since this wasn't smack dab in the middle, it took a little less than a half hour for Aldebaran, the eye of the bull, to pop out the other side. Again, this was a lunar occultation. In this case, a lunar occultation of a star. And today's program, if you think about it, is also about a lunar occultation of a star, isn't it? But in this case, the star we're talking about is a little closer to home. Our own favorite star, of course, I'm talking about the sun. And in this case, this type of lunar occultation of the sun has its own name, and that is, of course, a solar eclipse. This particular image that you see here is of the 2017 total solar eclipse, where the path of totality went right through Nebraska. This is a picture I took the moment before the sun, or rather the moon, completely covered up the sun, and we can see what is commonly called the diamond ring effect. This also happens when it moves back off again. If you get a chance to see this upcoming eclipse, if you get a chance to travel to within the path of totality, you too might get a chance to see and even capture this wonderful diamond ring effect. Three things must take place. Three things must be true for an eclipse, a solar or lunar eclipse, to take place. Number one, it must be eclipse season. Now, this may be a term that you haven't heard before. It's not really bandied about too terribly often. Eclipse season really comes down to the position not only of the Earth around the sun, but also the position of the moon's orbital inclination, its own tilt. And we'll be discussing this whole thing in much more detail in just a moment. Number two, the moon must be in the correct phase, or more technically speaking, it must be in its correct position in its orbit around the Earth. And because that position also determines the phase that we see, ostensibly it's okay to just talk about the phase that it's in during an eclipse. And then the last, number three, the viewer must be in the right place at the right time. So let's take a look at each one of these three things. First, I'd like to mention something that brings us all together. The sun is illuminating the moon and the Earth and all the planets in the solar system. And because we have just one source of illumination in our solar system, at any given time, half of the Earth is illuminated. Half of the moon is illuminated. It doesn't matter where it is. Half of all the planets in our solar system is illuminated. So unless you're Luke Skywalker at Tatooine with two suns in the sky, you might experience something differently. But in our own solar system, one light source, and therefore these are all one half illuminated. And again, it doesn't matter where the moon is around the Earth, half of it will be illuminated at any given time. But wait a minute, that's not what we see, is it? From our point of view, we see the moon go through different phases, very thin crescents, getting fuller and fuller and fuller, gibbous moons, all the way to a full moon, completely illuminated. So what's going on? Well, what we are seeing as a phase is, from our point of view, observing that one half illumination from different angles. For example, if the moon were here, half of the moon is illuminated, of course, but the phase we would see would be new. You'll notice you can't see anything. And that's because the opposite side, furthest away from us, is being illuminated. The near side is not. So the moon is up at the same time the sun is, so it's lost in the glare of the sun and we're unable to see it. About 14 days later, however, it's on the opposite side of the earth, and now it is completely illuminated from our point of view. The one half of the moon is the half that's facing us. And here we see a full moon. At a right angle to the earth, we have our quarter moons, first quarter and third quarter moons, which I know is an odd thing to call it, considering half of the moon is illuminated, but there's no such thing as a half moon, it is a quarter moon. This is called a first quarter moon because it is 1/4 of its orbit around the earth. And from our point of view, here in the northern hemisphere, the right half of the moon is illuminated. Down here at a right angle is a third quarter. It's also sometimes called a last quarter moon. From our point of view, it will be, well, light on the left. And as you can see, it looks light on the left here on this particular image. It is called a third quarter moon because it is 3/4 of its orbit around the earth. If we fill in the blanks, we see our waxing crescent moon, our waxing gibbous moon getting fuller and fuller going towards a full moon. We have a waning gibbous moon and a waning crescent moon as it's getting smaller and smaller, less illuminated, going towards a new phase. Now, if one were to take a look at this model, particularly with the moon in this position and the moon in this position, it's easy to make an assumption. That assumption being that the moon's shadow would cast upon the earth. In this case, the earth shadow would cast upon the moon. We should have a total solar eclipse and a total lunar eclipse once every month. But of course we don't. Why is that? Well, this model is not quite accurate. On this graphic, we have our moon. It's a little oversized. We actually need to make those a little bit smaller. We'll get rid of all that. The moon is 1/4 of the size of the earth. And then, of course, it's much further away than what we see here. The moon is 30 Earth diameters away. And 30 Earth diameters away the other direction, so the entire lunar orbit would be 60 Earth diameters across. That really gives you an appreciation of how big it really is, that particular orbit, and how far away it really is. You'll also notice it's slightly tilted. That's right. The moon's orbit has a very slight tilt along our plane by about 5 degrees. It doesn't seem like much, but that distance from us and that slight tilt, that makes all the change. This is why we do not have a lunar eclipse and a solar eclipse every single month, which of course would be pretty wonderful, but it just doesn't work out that way. Now, if we were to take a look at an orbital diagram like this from a polar point of view, it sure appears as if those two shadows intersect each other as the moon orbits the Earth. However, if we turn this on its side, we can see the truth. Most of the time, those shadows completely miss each other. But every once in a while, things line up just right, that the moon's shadow moves across the Earth, producing a total solar eclipse. Remember, number one, it must be eclipse season. And again, this has to do with not only the Earth's orbit around the sun, but also the position of the moon's orbital tilt. You will see here on the extremes of the ellipse that orbital tilt is such that the moon shadow and the Earth shadow, they will never intersect each other. They can't. However, here and here, where the axis is in line with the sun, this is called the line of nodes, it is now favorable for an eclipse. This is eclipse season. Now, it doesn't mean there will be an eclipse. It just means that it's favorable for an eclipse to take place, because you see, that's where number 2 comes in. The moon must also be in the correct position around the earth, and you can see it must be either a new or a full moon. The moon must be in the correct phase, more correctly, in the correct position around the earth. It must be a new moon for a total solar eclipse to take place. If it's not a new moon, you will not get an eclipse. It must be a full moon for a total lunar eclipse to take place. If it's not a full moon, you will not get a total lunar eclipse. As the moon falls within the shadow of the earth, we get to see a variety of different types of eclipses. It depends on whether it falls within this lighter portion of the shadow or this darker portion of the shadow. Now, I can demonstrate this, and you can demonstrate this in your classroom with a flashlight, and I'm going to make that as bright as I can and shine it on my hand, and you will see there's a lighter shadow around my hand. That lighter shadow is called the penumbra, and there's a darker shadow, that is the umbra. And as the moon falls within the penumbra, we get what's called a penumbral lunar eclipse. If, however, it dips its toe within the umbra, and that's it, we get a partial lunar eclipse. And if it moves completely within the umbra, that darker shadow, then we will get a chance to see a total lunar eclipse. As the moon travels within that umbra, it starts to disappear. Looks like it's being eaten away, like Cookie Monster, taking bites out of a cookie, disappearing more and more and more. And then once it's inside of the umbra portion of the shadow, something interesting happens. You would assume it would just disappear and not be visible, but actually, because of long wavelengths of light that are being conducted through the atmosphere of the Earth, shorter wavelengths are being stripped out, longer wavelengths then illuminate the moon, re-illuminate it with this rusty, reddish-orange color, which is the reason why sometimes it goes by kind of a spooky name. Sometimes it's known as a blood moon. So now we know that for a lunar eclipse to take place, it must be a full moon, and the moon must be on this side. However, during a solar lunar eclipse, or rather a solar eclipse, the moon must be on the opposite side, and it must be a new moon. Again, if it's not a new moon, we're not going to get a solar eclipse. And in this case, the shadow of the moon falls upon the earth. And once again, it's broken into 2 parts, a larger umbra and a very, very fine region at the bottom of a cone of dark light. That's the umbra. It produces a small line that crosses the earth at thousands of miles an hour. This transcribes the path of totality. And this brings up number 3. The viewer must be in the right place at the right time. During a solar eclipse, if you are on the earth, anywhere within the penumbra, you have a chance to see a partial solar eclipse. And the closer you get to the path of totality, the greater the percentage of obscuration is. And once you're inside of the path of totality, then you have a chance to see a total solar eclipse. Now you'll notice here we had an annular solar eclipse. This is what happened in 2023, last year, when the moon orbits around the sun. Because the orbit is elliptical in shape, sometimes we have perigee, where it's a little closer. Sometimes it's an apogee, it's a little further away from the earth. So during an annular eclipse, the moon is not only a new moon, but it's also near apogee. And because of that, the angular size of the moon is a little smaller, and it's not big enough to completely cover up the sun. So we get a ring of the sun around the moon called an annulus, hence the term annular solar eclipse. So that was sort of our pre-show for this wonderful total solar eclipse that we have this year. Here we can see the paths of totality for eclipses in the last, 24 years, from 2001 to 2025. These paths of totality can be as thin as a few miles and as thick as a few hundred. They're usually between 70 and 125 miles. Luckily, however, they can be thousands of miles long, giving the opportunity for millions of people a chance to see a total solar eclipse. Right here, we can see the path of totality for the April 8th, 2024 eclipse. Let's take a look at another view. This map, by the way, I have printed these out onto some really nice cardstock, and these are available either from myself or from NASA Nebraska Space Grant. So if you need some, contact me or contact Melissa or Michaela at Space Grant, and we'll see if we have some of these in stock for you to hand out to any students that you might have. I've also included the percentage of obscuration that you would see here in Nebraska. The path of totality is traveling diagonally from one side of the United States to the other. The path of totality for the April 8th eclipse is 115 miles wide, spans diagonally over 2,000 miles from Eagle Pass, Texas to Holton, Maine. The moon's shadow will travel between 1,500 and 3,000 miles an hour. And if you happen to be within that path of totality near the center, you'll get a chance to see a total solar eclipse for about 4 minutes. But I'll tell you, it's totally worth it for those 4 minutes. Where do you need to be able to see it? Well, of course, anywhere along that path of totality, but here are the larger cities or cities that are best placed along that center line of that path of totality. Dallas, Texas, Waco, Texas, Little Rock, Arkansas, Poplar Bluff, Missouri, Carbondale, Illinois, Indianapolis, Indiana, Cleveland, Ohio, Buffalo, New York, Montpelier, Vermont, and Holton, Maine. The ones that I highlighted in yellow are the ones that are closest for us that are here in the Omaha-Lincoln area. I actually measured it from Ashland, smack dab in the middle, to give us an idea of where the closest places would be and how long it would take. Just in case you want to pack a bag and head on over and take a look at a total solar eclipse. Little Rock, Arkansas at 9.5 hours. It would about 625 miles. Both Poplar Bluff, Missouri, and Carbondale, Illinois are about 550 miles, 8.5 hours away. You could travel to any of these places. And this brings up another point. Any of the hotels within this path of totality are probably already booked. And if you're lucky enough to find a hotel in this region, they are extremely expensive. Even Motel 6s and Super 8s are $800 and $900. It's really something else. So if you have any family or friends anywhere along the path of totality, maybe politely invite yourself over and then take everyone out to enjoy this wonderful eclipse. Another option, of course, is to get as close as you can to the path of totality and then find a little less expensive hotel somewhere there, and then the next morning drive on into that path of totality. And this brings up yet another point. Always keep your eye on the weather. Never assume the best location. You need to have your go bag. You need to be ready to head out in any location along the interstate and get to a place that hopefully will be clear for your observation. Now, of course, I know not everybody is going to be able to just pick up everything, pack a bag, and head on out to observe totality. Some people are going to be, well, stuck right here in Nebraska, and hey, there's nothing wrong with that. Just stay here and enjoy a beautiful partial solar eclipse. Here we can see the percentages of obscuration as we get further and further away from the path of totality across Nebraska, from 60% to 80%. Both Omaha and Lincoln will enjoy 80% coverage of the sun. Here I have some more information, and this is the information that can be found on this particular card. Alternatively, we also have a PDF that we can send to you that you can print out, or you can just jot down this information. In Omaha and Lincoln, it will begin around 1240. This is when the moon will start to obscure the sun. The maximum obscuration of 80% will take place around 2 o'clock. So 1:55 in Omaha, 1:53 in Lincoln. And then 2.5 hours after the entire thing starts, it will end at 3:10. On the opposite side of Nebraska, here around Scotts Bluff, you can see the times are considerably different, not only because of the distance away from Omaha and Lincoln, but also we're in a different time zone. We're in the Mountain Daylight Time at this particular time. It will begin at around 11:30 and end almost at 2 o'clock. You can see the obscuration is considerably smaller at 63%. Still absolutely worth heading on outside, particularly with any students or family, to check out this amazing, amazing event. So, how do we observe an eclipse? How do we observe the sun? Of course, as you probably know from the last eclipse in 2017, these total solar eclipse glasses have really become very, very popular. And even though they're called solar eclipse glasses, they can be used at other times to safely observe the sun. Well, these glasses have an aluminized mylar film that blocks out 100% of the infrared, 100% of the ultraviolet, all the harmful stuff, and then it cuts down the actual intensity of the sun by 10,000 times, allowing you to safely observe the surface, the photosphere, the visible surface of the sun. Now, a few points that I'd like to make. When you are using the glasses, be sure you look down before putting them on, put on the glasses, and then look up at the sun, and then conversely, look down, and then take them off. If and only if you are somewhere within the path of totality and you have the opportunity to see a total solar eclipse, during the moment of totality, for those 4 short minutes, you can take off the glasses and observe the beautiful corona around the sun. But the moment you see the sun peeking out from the side of the moon, be sure to get those glasses back on again. A few other safety notes. Do not use the glasses in concert with a telescope or a pair of binoculars, because now you're concentrating the light for an amount of light that these filters were not made for. Solar filters always need to go on the objective, and it's good to have a full filter on that particular objective. We'll talk about that momentarily when we talk about these different types of telescopes. Also, with children, those glasses can, well, not fit on the face very well. They can fall off, or the kids might peek. So here's a really nice activity that you can do. This is a wonderful modification for kids, and I've got mine right here. So you can see I've also done a little bit of artwork. We take a paper plate and we trace the glasses flat like this. We trace that. We then cut a nose piece and a mouth piece out. This is as much art as it is science, so you won't have any problem creating this. We then cut a rectangle out that's a little bit smaller than your trace. On either side of that rectangle, on that traced line, we place 2 slots that allow the arms of the glasses to come through. And now, once it's made, we have something that will protect a child from viewing above or below the nose line. Also, if you put some string on here and here, you can tie it on there and then it won't fall off the face. And then lastly, in an effort to put the A in STEAM, to put a little bit of art into the project, we've let our student design this with some neat sun motifs or whatever they want to do. And I think a great idea is to actually put the eclipse date on there so this becomes a keepsake for the rest of their lives. A wonderful little activity that you can do with students. Now, before the Mylar film, these filters really became popular. Before that, people were using the pinhole effect called camera obscura. I remember doing this when I was a little kid, and we did this with a shoebox similar to this. Now, on the top image, they just have someone with two paper plates, and they just put a hole in one paper plate and then moved it away from the other paper plate. Because of this camera obscura effect, you need no lenses here, as long as you have a small enough pinhole, and there lies in the issue with the pinhole method. It will produce a very, very small projection, no matter how far away you get, and as you get farther away, the projection gets fainter and fainter. With the two plates, the first plate here with the hole in it actually provides a shadow that the other one falls within, so it's a simple method. The shoebox method is the one that's been around forever, and it's the one that I did, and here they did something very clever. Right here, instead of using a tiny hole in the cardboard, they cut a larger hole and then put on a piece of foil. Then you can poke the foil, and the foil holds a better, more circular hole. Again, be sure to test this out. You don't want that hole to be too big or the effect doesn't work. Down here they're using a little paper dispenser tube from toilet paper, but the problem with this whole thing is, of course, how small that image is projected. So I used the same concept and created this design. Here I'm using a paper roll from wrapping paper, and it's much longer, and it produces a nice image in the bottom end that's a couple centimeters in size. So what I've done is I've plugged both ends. I plugged this end with a white piece of paper, I plugged this end with the foil, and I've just poked it with a pin to make that pin hole. In the side, I've cut open the entire side, left a little bit of the cardboard there so it produces a shadow, and then you stand here with the sun at your back, place that on your shoulder, you peer downward into the bottom of the tube, and then you slowly move around. Everybody needs a little practice with this until you're able to see the sun being projected on that white piece of paper. Another great way to do it, particularly if your school system is not allowing the solar eclipse glasses to be used. Again, this tube could be designed upon by the students. It's an excellent, excellent method. Here's another way to do the pinhole. You might look a little bit silly, but by putting the box on your head, you're in a little more darkened area, kind of that dark room effect, and now that faint image can be a little bit larger and easier to see. Besides the pinhole projection method, astronomers have also used optical projection as well, using a telescope or using a pair of binoculars. Now in this case, you would place your telescope, it should be on your mount, on your tripod. An eyepiece would go here. You're not going to want to use a Newtonian here. You're going to want to use just a standard refractor, relatively short focal length refractor. Point that at the sun, and then through the eyepiece, you can then focus this and project a very nice, large, high definition image. Some people have done the same thing with just a common pair of binoculars, but instead of using both of the oculars, they'll just take off the dust cap off of one side and do the same thing. Project this down, producing that high quality image that you can then focus. Now I imagine, particularly if you're a parent or a teacher, you can see a flaw with this particular system. You need to be extraordinarily careful, because the absolute last thing you want is for someone to observe through that telescope or through those binoculars. So astronomers came up with a few very clever ways to do optical projection in a very safe manner. For example, here we have what's called the sun funnel. And I even have a URL right down here. It's tinyurl.com/build-sun-funnel. I also mention again a little bit later. This is a device that produces a rear projection screen system. It's essentially a funnel from Walmart, cut down a bit, an eyepiece that you should already have, 10 to 15 millimeter eyepiece, which is placed on there with a pipe fitting collar. And then on the other side, some rear projection material, which can be nothing more than some gray, not white gray, it's a little bit better, shower curtain material. This is the liner material that you can get at Walmart for just a couple dollars. You cut a small piece, place that on the end, and now you get a safe rear projection view of the sun and any sunspots that you might see. And of course, partiality and totality during that total eclipse. A commercial product, and if you are an educator, you've probably seen these sun spotters. You might even have one within your equipment. This is a optical projection system, but the optical path is within the small triangle. It takes that light, goes through a lens, bounces off of a mirror, and it's in this area producing a nice large image in a very safe place, on a little area where you can place a piece of paper and you can have your students draw the sun, draw the eclipse, draw any sunspots. This is a fantastic way to go. However, the price for these is a little on the higher end, but it is a beautiful piece of equipment. There are now some telescopes out there, some electrical augmented astronomy telescopes out there that are about the same price, that actually come with a solar filter, and then you would observe the sun safely on your iPhone or your iPad. Speaking of telescopes, that brings us to perhaps the best method for observing the sun, and that is with a telescope with a white light solar filter or a dedicated solar telescope. So you can take a regular telescope like this and then place a white light filter, either a glass filter or a mylar filter on the other end. You just want to make sure that it's snug and safe, and then you're able to view the sun through the eyepiece, through your diagonal, and have an absolutely amazing view of the photosphere of the sun, which would allow you to see sunspots, maybe some granulation, and then of course the partiality and the totality once that happens. Although a little more expensive, another fantastic option are hydrogen alpha solar telescopes that look at a very narrow bandwidth of the electromagnetic spectrum that is correlated to burning hydrogen, and allows you to look at the chromosphere of the sun, where you can see granulation, you can see spicules, we can see some hotter areas, we can see some prominences as well. And then how wonderful would it be to view the eclipse through a hydrogen alpha solar telescope. Years ago, I traveled around Nebraska and actually passed out some Coronado brand personal solar telescopes to different school districts, and who knows, you might be within one of those districts that has one of those solar telescopes available. So here it is. Here is a total solar eclipse. This is why we do it. This is why we travel hundreds of miles, and some people travel thousands of miles and spend a lot of money to be able to see this and to feel this. Those of you who had an opportunity to see the total solar eclipse in 2017, you know what I'm talking about. You might have to look back and remember that moment of totality when the moon moved over the sun's disk. It's incredible. The sky becomes dark. The stars come out. The corona becomes visible. You can hear birds chirping. You can hear the crickets chirping as well. It gets noticeably colder. And what's amazing is how it hits you on kind of a strangely personal level. It's almost as if the universe is speaking to you. It's really an amazing, amazing thing. And this is why a number of people get bit by the eclipse bug and travel all over the world to see these things. During the total solar eclipse, you'll get a chance to see things that many people have never had a chance to see, including the corona, the outer atmosphere of the sun. This is the only time you can safely look at the corona is during totality, during, in this case, those 4 short minutes. We also see this reddish-orange area around the sun. That would be the extreme outer chromosphere. And then extending off of that are the solar prominences. Not solar flares, those are solar prominences. And you can just barely see them. They look like a tinge of color around the disk of the sun. And if you get a photograph, you can see those solar prominences very, very easily, much like we see in this particular photograph. You will remember earlier, I mentioned a planetary alignment, a very special planetary alignment. It's taking place during the total solar eclipse. So if you happen to be within totality, when it gets dark, not only will the stars appear, but some planets as well. First and foremost, Venus will pop out because it's so extremely bright in the lower right. In the upper left, we have bright Jupiter as well. Those you will easily be able to see. A little lower on the horizon in the southwest, Saturn and Mars will also become visible. And if you have really good eyes, you may even be able to catch elusive Mercury here, which is very difficult to see. Many astronomers have never had a chance to see Mercury. Normally, you need to go on out right before the sun comes up in the east or right after the sun goes down, and only during certain times of the year when Mercury is at greatest elongation. But here, you'll get a chance to see maybe Mercury, Jupiter, Venus, Saturn, and Mars during the day and during a total solar eclipse. Here are a few other things that you might want to look for that are particularly interesting. These are great activities for students. These are great activities for anyone. The first one here are called atmospheric gravity waves, or more precisely, the clouds created by atmospheric gravity waves. Now, let me say very quickly, this has nothing to do with gravitational waves. Gravitational waves are ripples in space-time. It's a whole different thing. An atmospheric gravity wave is when these striated layers of atmosphere, under the correct conditions, they're forced upwards into other layers. We might have layers that are a little bit filled with more moisture, and as they're forced up into cooler areas, they can then produce clouds, condense into a line of clouds, but then it falls again due to the force of gravity, and then back up again, producing another line of clouds, then down, then back up again, and it creates this wave that goes through these striated layers of atmosphere, creating clouds that look like this. This normally happens during very specific times under just the right conditions. It can also happen around mountains where air rushes up mountainsides, so the terrain can have something to do with it as well. But it turns out that atmospheric gravity wave clouds can also appear during solar eclipses. So, if you are near the path of totality or within the path of totality, keep your eyes open for any clouds nearby and take a look for these zebra-like striations. You may have seen an atmospheric gravity wave cloud. We have another interesting phenomenon that has been observed for years and years called shadow bands. Now, I'm going to start a video here, and I'll tell you now, it's hard for me to see, and I imagine it's going to be very difficult for you to see as well, but you might see a shimmering effect going on this video. It's very subtle in any video that you may see. In real life, Your eyes are just a little bit better at seeing this. It's still subtle, but in real life, you'll be able to see it. As the light comes in through the atmosphere, through some areas of turbulence, it creates these ripples. And it specifically is happening the moment that the moon is covering up the sun, and then the moment it moves back around again. So as the moon gets closer and closer, covering up the disk of the sun, that thin crescent of light is essentially collimating, becoming more focused, and then creates these waves that are sometimes called shadow bands. So if, and again, only if you are in the path of totality and you're traveling along to see the total solar eclipse, take a large piece of white cardboard or even just a white sheet with you. Put it down on as flat of a surface as possible, and then keep your eye on that. Maybe even have someone videotaping that as the totality is taking place. And maybe, just maybe, you too will capture shadow bands. The last one here can be for anyone, whether you are in the path of totality or outside of the path of totality, are natural pinhole projections. You'll remember our camera obscura, our pinhole projection method. Well, nature can do this as well. As light shines through the small openings between leaves, it can project hundreds and hundreds of tiny eclipses down on the ground. So keep your eyes open for these during an eclipse and take a picture, because what a wonderful, wonderful memento of that fantastic event. There are some notable scientific discoveries and observations that have been made during eclipses, and still to this day, a great amount of research is being done. Here are some of the most popular things, and we're going to start way, way back in 384 to 322 BC. Aristotle recognized the spherical shape of the Earth during lunar eclipses. So looking at the shadow of the Earth upon the moon was always curved regardless of the time. In other words, the only way that it could always be curved, the same curve, never a straight line, is if the Earth was spherical. About 300 years later, Aristarchus, a whole nother fellow, of course, was able to infer the comparative sizes of the moon and the Earth during these eclipses. Not the exact size of the moon and the Earth. Actually, someone did do that as well. And he was also able to determine the relative size of the sun. So these fellows, thousands of years ago, knew that the Earth and the sun and the moon were spherical. They knew the relative sizes of these things. They knew that the Earth was larger than the moon and that the sun was larger than the Earth. They were very, very clever fellows. Nearly 1,000 years later, 968, Leo Diaconus was the first to record an observation of the sun's corona. Now, of course, he wasn't the first to see the corona around the sun, but he's the first to put pen to paper and talk about this outer atmosphere of the sun. And speaking of that atmosphere is one of my favorites. In 1868, Pierre Janssen and Joseph Lockyer discovered the element helium by analyzing the sun's corona. Now get this. Helium, that gas that makes your balloons float and your voice sound funny. That gas, that element that is the second most abundant element in the entire universe, was not discovered here on Earth first. It was discovered on the sun via spectroscopic analysis of a corona during a solar eclipse in 1868. Then later, it was discovered here on Earth. Because it was discovered on the sun, they named it after the Greek god Helios, hence the name helium. And then the last, which is perhaps most important for modern physics, is in 1919, Frank Dyson and Arthur Eddington were able to perform observational tests of Einstein's theory of general relativity. Just a few years earlier, Einstein came up with this amazing concept, this theory of essentially curved space-time. And they were able to actually measure a deflection of light caused by the mass of the sun in the night sky. And they were able to then prove Einstein's theory at that time. We're still doing research to this day. NASA has an amazing project called the Nationwide Eclipse Ballooning Project. My wife and I are a couple of the leads for the Nebraska contingent. That's us right here. And along with 50 teams from 40 different states around the entire United States, we are all launching high altitude balloons within the path of totality. These high altitude balloons are like weather balloons, and they get up to 75, 85, 95,000 feet. They analyze the temperature and the pressure, and they have cameras on board. We are going to be trying to live stream the view from these balloons of the shadow as it passes across the earth, putting that on the internet, allowing people to observe this from all over the world, observe it live. So let's end today's program with a few numbers here and a few quick questions. Are total solar eclipses rare? Yes and no. It kind of depends on how you look at it. You see, total solar eclipses take place on an average 1 in every 18 months. That's right. 1 every year and a half or so, we have a total solar eclipse. That doesn't seem right, does it? The next total solar eclipse is in only a couple years, but it's 3,000 miles away on the opposite side of Greenland, so it'd be quite a trip. But they are also rare if you do not want to move. If you just want to stand there and wait for an eclipse to come to you, the odds of seeing a total solar eclipse from where you live is 1 in every 375 years. So it is very special that we've had the opportunity to see an eclipse going right through Nebraska in 2017 and another one going through the United States this year. When was the last total solar eclipse? When is the next? Well, of course, the last one was in 2017, 6.5 years ago. It's hard to believe it was that long ago. It seems like yesterday to me. And before that, it was in 1979, 45 years prior. After the total eclipse on April 8th, the next total solar eclipse that's going through the entire United States is in 2045. Whew. Technically, there's a total solar eclipse visible in the United States in 2044, a year earlier, but it's only going to be for the Dakotas. But this one is going to go right through the middle of the United States. I don't know about you. I hope to still be around to view this eclipse, but the fact that it's not for a very long time really emphasizes the importance of getting out there and seeing this eclipse on April 8th. I've got a few fantastic resources here, and I don't expect you to write all these down. Right over here, I have a QR code. Let me come to the other side, and you should be able to scan that QR code with your phone via the video here, and that will give you a link to a website where I've listed some wonderful resources for anyone and everyone, also some fantastic resources for educators, including eclipse activities and some guides, and then some wonderful apps and some other things that you can use to view the eclipse that's coming up. I'd like to thank all of you for spending the time sitting there listening to this program. I certainly hope you found some very, very valuable information to enrich your life and to enrich the life of your family members and your students if you're an educator. Once again, thanks so much. My name is Michael Sibbernsen with Branched Oak Observatory. Thank you so much.